Put on a pair of headphones for a second and imagine this. A low, droning tone. Not quite a hum, not quite a whistle. Something in between, rising and falling so slowly it almost sounds like breathing. It isn't music. It isn't static. It's the actual sound of the space between the stars, captured by a machine humanity built in 1977 and then let go of, forever, into the dark. And here's the part that should genuinely unsettle you. Nobody can tell you exactly what the sound is hearing right now, this second, because by the time any signal from that machine reaches us, it's already almost a full day old. We are not watching this happen live. We are watching the past arrive, one whisper at a time, from 15 billion miles away. That machine is Voyager 1, and what it's been quietly recording for the last decade and a half might be one of the strangest, least talked about discoveries in the entire history of space exploration. Let's get the basics straight first, because the scale of this story doesn't land until you understand just how absurd it is that this spacecraft is still working at all. Voyager 1 launched in September of 1977, a few weeks after its twin, Voyager 2. Both were built to do one job: fly past Jupiter and Saturn, take pictures, and send them home. That was the mission. That was supposed to be the whole story. Instead, Voyager 1 discovered new moons around Jupiter, found a faint ring system nobody knew was there, photographed the haze-choked atmosphere of Saturn's moon Titan, and then, having technically finished its job, just kept going. It kept going past Saturn. It kept going past the orbit of Neptune. It kept going for so long and so far that in February of 1998, it overtook Pioneer 10 to become the most distant human-made object in existence, a title it still holds today, more than 2.5 decades later. In 1990, at the direction of astronomer Carl Sagan, Voyager 1's cameras were turned around for one final look backward before they were shut off forever to save power. From roughly 6 billion kilometers away, it photographed Earth as a single point of light, barely a pixel, caught in a scattered beam of sunlight. Sagan called it the pale blue dot, and used the image to argue that everything humanity has ever fought over, built, or believed in happened on that one speck of light, alone in the dark. Strapped to the side of the spacecraft that took that photo is a golden record, etched with sounds and images meant to represent life on Earth, greetings in dozens of languages, whale songs, a baby's cry, snippets of music from across human history, just in case, against every reasonable odd, something out there ever finds it and wants to know who sent it. On August 25th, 2012, Voyager 1 did something no human-made object had ever done. It crossed the heliopause, the outer edge of the bubble of charged particles and magnetic field that our sun blows out around the entire solar system, like a bubble of breath in cold air. Past that boundary is interstellar space, the actual material between stars, not science fiction, not a metaphor. Real, true interstellar space, and Voyager 1 was suddenly sitting in it. Here's where it gets strange, though, because at first, nobody could prove it had actually happened. The spacecraft's plasma instrument, the one designed to directly measure the density and speed of charged particles around it, had stopped working decades earlier, broken since 1980. Without it, scientists had no direct way to confirm Voyager had actually left the sun's bubble. They were flying blind, watching other measurements shift in ways that looked right, but they didn't have the one piece of hard proof that would settle it. Then, almost by accident, the sun helped them out. In March of 2012, a massive eruption on the sun's surface sent a shockwave rippling outward through the solar system. It took about 13 months to reach Voyager 1, arriving in April 2013, more than a year after it left the sun, and roughly 8 months after Voyager had crossed the heliopause. When that shockwave slammed into the plasma surrounding the spacecraft, it didn't move the broken plasma instrument. It rattled a completely different one. The plasma wave subsystem, a pair of long antennas designed to detect oscillations in charged particles, picked up the vibration like a tuning fork struck across an unimaginable distance. And what those oscillations revealed, when scientists ran the numbers, was the density of the plasma surrounding Voyager 1. It was roughly 40 times denser than anything found inside the heliosphere. That density was the fingerprint. That was the proof. Voyager 1 wasn't just near interstellar space. It was inside it, and had been for almost a year already without anyone being able to confirm it. Now here's the part that turns this from a data point in a journal into something you can actually experience. Those oscillations the plasma wave instrument detected aren't sound, not in the way your ears understand sound. There's no air in interstellar space for sound waves to travel through, no medium for compression waves to move across the way they do when someone speaks to you in a room. What Voyager 1 actually detects are electromagnetic vibrations and charged particles, oscillations with a frequency far too low for any human ear to register on its own. But frequency is frequency, whether it's electromagnetic or acoustic, and NASA scientists realized they could simply shift those oscillations up into the range of human hearing. The same basic idea as slowing down or speeding up a recording, until a pitch becomes audible. That process is called sonification. It isn't artistic embellishment. It isn't a sound designer adding ambience for a documentary. It's raw plasma wave data from billions of miles away, translated frequency for frequency into something your ears can actually process. When NASA released the resulting audio publicly, first in 2013 and again in expanded form years later, what people heard was an eerie, rising and falling tone, somewhere between a whistle and a drone, unlike anything recorded by any instrument before it. It is, as close as humanity has ever come, the actual sound of the space between stars. It's worth being precise about what you're hearing when you listen to that clip, because the eeriness of it is real, but it isn't supernatural, and it isn't manufactured for effect either. Each rise and fall in pitch corresponds to a genuine change in the density of the plasma Voyager was passing through at that exact moment. Denser plasma producing a higher pitched oscillation, thinner plasma a lower one. When the recordings went public, plenty of people online assumed NASA had added music or dramatized the audio for an anniversary press release. They hadn't. The pitch shifting is the only liberty taken simply to drag inaudible frequencies into a range your ears can register, and underneath that shift, every wobble and waver in the tone is raw measurement, the literal, unedited fingerprint of matter Voyager 1 was physically moving through at the time, recorded by an instrument designed during the Nixon administration. For years after that 2013 confirmation, the working assumption among scientists was that this plasma activity was an occasional event, something that happened when a solar eruption, traveling for over a year across billions of miles, finally slammed into the interstellar plasma around Voyager and rang it like a bell. A rare, dramatic encounter, followed by long stretches of silence in between. That assumption held for almost a decade. Then, in November of 2018, something remarkable happened that had nothing to do with luck or timing. Voyager 2, traveling in an entirely different direction than its twin, crossed its own heliopause and entered interstellar space independently. For the first time, scientists had two separate spacecraft, on two separate paths, both confirming the same basic structure of the boundary between our solar system and the galaxy beyond it. Voyager 2 still had its working plasma instrument, the one that had broken on Voyager 1 decades earlier, and it measured a sudden dramatic jump in plasma density right at the crossing, exactly the kind of signature scientists had inferred indirectly from Voyager 1's plasma wave data years before. Two independent machines, launched weeks apart in 1977, drifting apart for 41 years in completely different directions, arrived at the same physical conclusion about where the sun's influence actually ends. That kind of agreement, separated by decades and billions of miles, is about as close to ironclad proof as space science ever gets. Then, in 2021, a team of researchers at Cornell University, led by astronomer Stella Koch-Ocker, went back through years of Voyager 1's plasma wave data, looking for something nobody had specifically searched for before, a continuous signal rather than isolated bursts triggered by solar storms. What they found, published in the journal Nature Astronomy, quietly rewrote what scientists thought they understood about interstellar space. The hum wasn't occasional, it was constant. Underneath the loud, dramatic spikes caused by solar shock waves arriving years after they erupted, there was a faint, persistent, ongoing drone, present in the data essentially all the time, with no external trigger required at all. It was less like an occasional clap of thunder and more like rain that never quite stops falling, a low murmur running continuously through the gas that fills the space between stars. Think about why that actually matters, beyond how eerie it sounds. If the activity were only triggered by rare solar outbursts, scientists would only get a glimpse into the interstellar medium once every few years, whenever the timing happened to line up. A persistent hum means something completely different. It means Voyager 1 has effectively become a continuous microphone, capable of measuring the density and structure of the gas around it at almost any moment, not just during rare dramatic events. Researchers can use that ongoing signal to map out subtle variations in the density of interstellar gas as Voyager drifts through different regions, something closer to a submarine, using ambient sonar to read the water around it than a single ping bouncing once off a passing object. It turned an occasional, lucky measurement into an ongoing dataset, and that dataset is still the only direct first-hand account of interstellar plasma conditions that our species has ever collected, because no other spacecraft has ever traveled far enough to listen in the same way. It's worth pausing on just how small that low-level hum actually is. The persistent emission Ocker's team identified is extraordinarily faint, only a fraction as intense as the dramatic shockwave events that first confirmed Voyager had left the solar system back in 2013. Extracting a signal that's subtle out of 40-year-old instrumentation, originally engineered in the 1970s to study the much louder plasma environments around Jupiter and Saturn, and never designed with this kind of long-term interstellar listening in mind, is itself a small miracle of patient, careful data analysis. Nobody who built the plasma wave subsystem in the 1970s was thinking about interstellar gas at all. They built it to study the turbulent, noisy plasma whipping around the gas giants during 2 brief flybys that were each supposed to last only a matter of months. The fact that the same hardware turned out to be sensitive enough decades later to pick up a whisper-quiet hum in a completely different region of space it was never designed to explore is exactly the kind of lucky over-engineering that has kept this entire mission alive for almost half a century longer than anyone originally planned. Which brings us to right now. Not 7 minutes ago, not breaking news from this afternoon, but a genuinely live, ongoing situation that's unfolding across this entire year. Voyager 1 is dying slowly, the way it was always going to. Both Voyager spacecraft run on radioisotope thermoelectric generators, devices that turn the heat from decaying plutonium into electricity. And that heat has been fading bit by bit since the day they launched. Each spacecraft loses roughly 4 watts of power every single year. After nearly 49 years in flight, that slow bleed has become an existential problem. There simply isn't enough power left to run everything anymore, and the team at NASA's Jet Propulsion Laboratory has spent years deciding, in advance, exactly what gets switched off and in what order. So they're never forced to make that call in a panic. On April 17, 2026, that list caught up to one of Voyager 1's last remaining science instruments. Engineers sent a command, one that took roughly 23 hours just to reach the spacecraft, to shut down the low-energy charged particles experiment, an instrument that had been running almost continuously since 1977 and had spent decades helping scientists understand the structure of the solar system's outer edge and the interstellar medium beyond it. The same instrument had already been switched off on Voyager 2 a year earlier. With it gone, Voyager 1 was left with only 2 functioning science instruments out of the 10 it originally carried. One measures magnetic fields, the other is the plasma wave subsystem, the exact instrument responsible for that hum, the one piece of equipment still letting us listen to the space Voyager is moving through. Of everything left on this spacecraft, the ears were judged too valuable to lose. Mission engineers have been clear that shutting down a working instrument is never an easy call, especially one that had been quietly running for almost 49 straight years without complaint. The scientists who built the low-energy charged particles experiment decades ago, now well into their careers studying its data, have said openly that they're holding on to hope the instrument gets a second life, that the work the team is doing right now to squeeze more power out of an aging spacecraft might let them keep learning from a region of space no other instrument anywhere has ever measured. That tension between an engineering team forced to make brutal trade-offs and a science team desperate not to lose a single sense the spacecraft has left is exactly the kind of quiet, unglamorous drama playing out in mission control rooms right now, far away from any headline. There's a possible second chance buried in all of this, and it's playing out as you're hearing this. Engineers have developed a workaround, internally nicknamed the Big Bang, a method to squeeze out additional power that's never been tried on either Voyager before. The plan is being tested first on Voyager 2 across May and June of 2026, specifically because it has slightly more available power and is somewhat closer to Earth, making it the lower risk option to experiment on first. If that test goes well, the same fix could be attempted on Voyager 1 as early as July. And if it works there too, there's a real chance the low-energy charged particles instrument, the one just switched off in April, could eventually be turned back on, buying this nearly 50-year-old machine a little more borrowed time at the edge of everything we've ever explored. Nobody at NASA is promising that outcome. The honest, repeated language from the mission team has been hope, not certainty. The kind of careful optimism people use when they've spent a career learning not to count on hardware built in the 1970s behaving the way they want it to, 4.5 decades and 15 billion miles after it left the launch pad. And then there's the milestone waiting at the end of this year. On November 18th, 2026, Voyager 1 will reach 1 light day from Earth, a distance of just over 16 billion miles, the point at which it would take a beam of light a full 24 hours to travel from the spacecraft back to us. No human-made object has ever been that far away. Commands sent up to it already take nearly a full day to arrive. To put that in perspective, when Voyager 1 launched in 1977, a round-trip message to the spacecraft and back took only a few seconds. Today, it takes nearly 2 days. By the time this video reaches you, whatever Voyager 1's plasma wave instrument is hearing right now has already happened, already drifted past, already become history before the data even leaves the spacecraft. That's not a flaw in the story. That's the actual scale of what we built, and what it's still doing alone, far past the edge of anything we can reach in real time. It also means something practical and slightly heartbreaking for the mission team. Every year, as the distance grows, the signal Voyager 1 sends back gets weaker, and the round-trip conversation between Earth and the spacecraft gets longer. Eventually, even if every instrument somehow kept working forever, there would come a point where the signal is simply too faint for even NASA's largest receiving dishes, the 70-meter antennas of the Deep Space Network, to pick it out from the background noise of the universe. Power loss and distance are working against this mission from 2 different directions at once, and engineers don't know which one will end the conversation first. Here's what makes all of this worth sitting with for a moment. Voyager 1 is going to go silent eventually. Maybe this year, maybe in a handful more, as the power finally runs out for good and the last instrument finally stops transmitting. When that happens, our only direct, ongoing window into the actual physical conditions of interstellar space closes with it, possibly for decades, possibly for far longer, until some future mission is built specifically to listen again. There is no second Voyager 1 waiting in a hangar somewhere, no quick replacement that could be launched next year to pick up where it left off. Anything that follows it would need decades just to travel as far as Voyager already has. Which means whatever data this aging, dying spacecraft sends back between now and its final transmission may be the only first-hand account of this region of space that anyone alive today will ever get to hear. Every additional month this nearly 50-year-old machine keeps running, every extra packet of plasma wave data it manages to send across that growing, day-long gulf of empty space is borrowed time on a discovery we may not get to make again for a very long while. No spacecraft launched since 1977, no matter how much more advanced its electronics, has had the time to travel as far as Voyager 1 already has. Distance, in this one specific case, can't be bought with better technology. It can only be earned with decades, and Voyager 1 already spent nearly 50 years earning the only vantage point of its kind that exists anywhere. Right now, somewhere out past the edge of the sun's influence, in a place colder and emptier than almost anywhere humans have ever sent a tool that still works, something is still humming. And for now, we're still listening. If stories like this are the kind of thing that actually keep you watching, the real ones, not the manufactured ones, that's exactly what this channel is for. Subscribe so the next one finds you, and share this with someone who needs a reminder that the strangest sounds in the universe are sometimes the realest ones.